Hi class, this is Sir Alex Basco and welcome to our lesson in General Physics 2. Today we are discussing the second part of Lesson 7 and we are going to finish basically Lesson 7 today, which is still all about Gauss's law. So let's go and start by first reviewing what discussed previously. So previously we've learned all about how to measure the electric flux on an enclosed surface. Remember, we used this equation wherein the total electric flux of a surface would be equal to the total of all the charges found inside the surface divided by the permittivity of free space, or epsilon naught. So we use Gauss' law when we want to measure the electric flux of an enclosed surface with a charge inside. Because remember, let's say for now, let's remove this. We don't have a charge inside our enclosed surface. If we have an electric field that is originating outside, we know that the total electric flux of a surface with an electric field outside would actually be 0, because the total amount of electric field that is passing going inside the surface and the amount of electric flux going out of the surface would actually be equal. So again, the amount of electric field going inside is equal to the amount of going outside. Therefore, the total electric flux is 0. And we can actually see these from the previous examples we had. If you remember, when we were solving for the electric flux of a cube, if you actually measure the total electric flux that each side of the cube is experiencing, you would actually end up with having a 0 total electric flux. Again, this is for a situation wherein the enclosed surface does not have a charge inside. But if your enclosed surface has a charge inside, similar to this sphere right here, then we can use the Gauss law to actually measure the electric flux. And we know that in order for us to do that, we just have to measure the magnitude of all the charges found inside. So the charges inside that surface could be just one, like this, or it could be even however was given to you. It could be 2 or 3 or 4 and etc. What you just need to do is add all the magnitudes of those charges and then divide it by a constant called the permittivity of free space. And if you notice from this equation that regardless of the shape of the surface, the size of the area of your surface, and even the position of the charges, the electric flux actually remains the same. So because if you again look at your equation, the shape does not affect the equation, the size of the area does not affect the equation, and even where the position are even where the charges are positioned inside does not affect your equation here, meaning the electric flux will remain constant. Now, the only thing that you have to worry about is that your enclosed surface has no holes, because once that enclosed surface has a hole in it, then the total flux would actually be different, because again there is a hole, so there is a space or surface wherein no electric flux is happening, or there is no electric field passing through that surface. So another thing is that again, regardless of these things, the shape of your enclosed surface, it could be a sphere, cube, rectangle, triangle, whatever, the size of that surface, or the size of the area of that surface, and the position of the charges, electric flux remains the same, as long as again there is no hole, and also the electric field remains the same, and there's something that what we call a symmetry on charge distribution that we will discuss later. So the electric flux remains the same because there's no hole, the electric field remains the same, and there is actually a symmetry of charge distribution. So what that means is that despite Gauss' law talking about electric flux, or meaning we use Gauss' law to measure electric flux, we can actually infer the electric field using Gauss' law. Meaning what we are going to do today is to use Gauss' law not to measure electric flux, but to actually measure electric field. Not to measure phi or phi. This is the Greek symbol for phi, which is what we use to denote electric flux, which is the passing of electric field onto a surface. But this time what we're going to do is to use the principle of Gauss law to infer electric field. This time we are measuring the magnitude of your electric field. So in order for us to do that, we have to understand a principle called the Gaussian surface. So again, even if Gauss law is not about electric field per se, it's about electric flux. Because it deals with electric flux, it is possible for us to use the principle of Gauss law to solve for electric field. I've just rehashed what I said earlier. And in order for us to do that, we have to identify what we call a Gaussian surface. So what is a Gaussian surface? Gaussian surface is basically an imaginary enclosed surface where we can actually compute or calculate the electric field from a we can actually compute the electric field. So later on I will show you how we actually figure out this Gaussian surface. But remember, in order for us to measure the electric field should have first, it should be consistent, and number two, which is a very important thing, it has to have a distribution of charge, or symmetry and distribution of charge. So what we're going to do is to first identify a symmetry and the distribution of charges. So there are three types of symmetry in our Gaussian surface. We can first create a physical symmetry or spherical symmetry. Second, we can create a cylindrical symmetry. And third, we can create a planar symmetry. And then for charge distribution, we can actually express charge distribution by first what we call a volume charge density. And the units we use for volume charge density is this is coulombs per meter cube. This is, I hope, easy to remember because volume is basically side times side times side. So if you think about these sides, or length times width times height, so as you can see, you can measure this in terms of meters, right? So when we talk about volume charge density, it's usually coulombs per meter cube. So the cube there tells us that this is a volume charge density. So the charge distribution is in volume, or is in terms of volume. There's another charge that and this is the equation for the volume charge density, where we have, this is what we call a rho. This is a Greek symbol for rho. Rho is equals to the charge, or the magnitude of the charge, divided by the volume of your enclosed surface. So your enclosed surface is in terms of volume. Then there's what we call a linear charge density. So from the word itself, linear or line, so we have a line of charges, and if we have a line, we can actually only measure that in terms of meters. And within that line, since it is only measured in meters, the units for linear charge density is in terms of coulombs per meter. As you can see, this is meter because it's only in line. Okay, and then there's another one, or this is the equation for linear charge density. We use the Greek symbol lambda. We call this lambda. So lambda is equals to the total charge divided by the basically the length of your line. Okay, and lastly, we have another charge distribution called the surface charge density. So surface, we are talking about area. And in order for us to solve an area is basically equal to length times width, or side times side. And as you can see, if we measure this in terms of meter, so surface charge density has a units of coulombs per meter cube, or meter squared. And the equation we have for surface charge density is sigma. This is the Greek letter for sigma. Sigma is equals to Q divided by the area of your surface. So I want you guys to remember this symmetry. We can create spherical symmetry, cylindrical symmetry, and we have planar symmetry. Another thing is we have in order for us to identify the charge distribution, we can use either volume charge density, linear charge density, or surface charge density. And later I will show you where we actually use these various equations of charge density. So let's begin first with our first spherical, for our first symmetry, called the spherical symmetry. Again, what we are doing here is we are creating a Gaussian surface to solve for the electric field. So in the end, our answer is basically an electric field. And in order for us to solve for electric field, we have to create a Gaussian surface that is in terms of a symmetry between with a symmetry and a distribution charge. So but first, before we go to discussing spherical symmetry, there's one thing that I want you guys to remember about. When we deal with spherical symmetry, we usually use it in terms of insulating versus conducting spheres or conducting objects, insulating or conducting objects. When we are talking about something that is insulating, something that I want you to remember, the charge of an insulated object is usually found inside that object. Therefore, if the charge is found inside, we have to use the volume charge density, because again, the charge of an insulating object is found inside the volume. Hence, again, we have to use the volume charge density, or with the has the units of coulombs per meter cube, and we use the equation rho. Is it rho? I believe it's rho. Yeah, rho is equals to Q divided by volume of your surface. And then we have what we call a conducting. If you have a conducting object in your problem, the charge of a conducting object is usually found on the surface of that object. And since this is a surface, we have to measure this in terms of surface charge density, or we have to measure the conducting object in terms of surface charge and density, meaning the unit is in coulombs per meter squared. And the equation for surface charge density is sigma. Yeah, I believe it's sigma is equals to Q divided by the area of your surface. So this is something that I want you guys to remember, okay? Because this will help you identify or how to solve the spherical symmetry, or how to solve for the electric field using the Gaussian surface in terms of spherical symmetry. Okay, now let's discuss spherical symmetry. So what I want you guys to start with is I want you guys to imagine we have a conducting sphere with a radius r. So imagine this circle right here as a sphere. So even though it's drawn into this space like a circle, I want you to think of this as a metal ball. And since this is conducting, remember what we just discussed earlier, the conducting part tells us that the charge of this object is in the surface. It's not inside. So usually you would notice that the conducting is usually hollow because the charge is found on the surface and not inside the object. So we have a conducting sphere with a radius r. So the charge of this object is on the surface. That's why they're around here. Therefore, the charge, because it is conducting. And then what we want to do is, what if we want to measure the electric field at a distance r1 from the center of the sphere? So this is the center of the sphere, and we want to measure the electric field at an r1, wherein the r1 is less than the value of the radius. So meaning the r1 is, let's say, about this length. So what is the electric field at this point? Okay, so before we measure that, let's think about this another situation. What is the electric field at a distance r2 from the center of the sphere if r2 is greater than the radius of your sphere? So meaning, since it's greater than, it is outside. So it basically breaks past the size of your conducting sphere. So what is the electric field at this point? So how are we going to measure this? If we have a sphere, something like this, it can either be conducting or insulating. In order for us to solve for the electric field at this point, or even at this point, this is where the Gaussian surface follows. Again, like I mentioned earlier, Gaussian surface is basically an imaginary surface that we can draw in order for us to derive the electric field. So what we are going to do to actually solve this, you have to create what we call a spherical symmetry, meaning you have to create a imaginary circle inside with a distance r, with a radius of r1. So meaning like that. So basically you want to draw a circle, an imaginary circle inside your conducting sphere, and then you can use this circle right here to actually measure for the electric field using the principle of Gauss's law. And then if you want to measure for the electric field at the distance r2, wherein r2 is greater than the radius of your sphere, then you actually have to create a Gaussian surface of a spherical symmetry, wherein you're enclosing the whole conducting sphere with an imaginary sphere with the radius r2, wherein at the surface here you're basically measuring the electric field. And then you have your since the conducting sphere, the charge of the conducting sphere are found on the surface. So I've just drawn the electric force line or force line to denote the electric field. So this is your electric field. So from this setup right here, how can we measure the electric field at this point, and what is the electric field at this point? So let's continue on. So for R1 has zero charge inside. So before let's go here, let's go back in this one. So what I want you guys to notice now is how can we measure the electric field for our first imaginary Gaussian surface, and how can we measure the first or our second Gaussian surface? Well, from the principle of Gauss law, remember in Gauss law, we use Gauss law to measure the electric flux with an enclosed surface that has a charge inside. Remember? So for example, let's not draw a box, let's draw a sphere. So if I have a sphere and this sphere has a charge inside, then I can use Gauss law to measure, because that's what Gauss law does. It measures the electric flux if an enclosed surface has a charge inside. Now let's look at this Gaussian surface that we have. So our first Gaussian surface is the one with an R1. Notice now, does this surface right here, or does this Gaussian surface right here has a charge inside? The answer is actually no, because the charges of the conducting sphere, your original sphere, not the imaginary sphere, they are all found on the surface, but this sphere right here is found inside. So basically, inside of this Gaussian surface right here, there are no charges because nasa loob siya. This R1 is nasa loob nung true sphere mo, nung conducting sphere mo, right? So alam natin sa conducting sphere, yung mga charges ng conducting sphere nasa surface lang nung sphere. nasa surface lang ng sphere yung mga charges, and may isa ka pang sphere inside, which is our imaginary Gaussian surface, you would know that there are no charges inside. Therefore, from here, you can actually already denote that the electric flux here is 0. And if the electric flux is 0, the electric field for R1 is actually 0. Alright? Now, let's look at our Gaussian surface R2. So we have our Gaussian surface, second Gaussian surface with a radius of R2. What you notice now is that this imaginary sphere, this green sphere, which is our Gaussian surface, it encloses your conducting sphere. It means found inside of this Gaussian surface are the charges. And remember what we do for Gauss's law. In Gauss's law, it measures the electric flux as long as your enclosed surface has a charge inside. And consequently, for our R2, the charges are actually found inside your R2. Therefore, you can actually solve for, or this has a electric flux is happening here. Therefore, you can actually measure the electric field here. So the question now is, how are we going to measure the electric field for this type of situation? And another thing before we do that, now I want you guys to notice that in such situation wherein you have a Gaussian surface with an radius, in terms of, this is in terms of spherical symmetry, if you have a radius that is less than, or if you have a Gaussian surface sphere with a radius that is less than to the radius of your either conducting or insulating sphere, the electric flux would automatically be 0. But if you have a Gaussian surface with a radius that is greater than the radius of your sphere, it gives you the idea that this sphere right here, this Gaussian sphere right here, has a charge found inside. Therefore, there is an electric field that you can measure for this type of situation. So let's continue. I hope you guys remember that and understand what I'm discussing. If there's anything that is confusing, please let me know, okay? But again, so these right here are your Gaussian surface. These are the imaginary surfaces that you created, and they are a sphere that is in symmetry with your conducting or sometimes an insulating sphere. And the thing though, this is only true for conducting spheres. You have a situation wherein you have insulating. For insulating sphere, remember, for insulating sphere, the charges are found inside the volume, which means even if your R1 is less than the radius of your insulating sphere, or your R2 is greater than the insulating sphere, for insulating spheres, you actually have an electric field for both that you can measure. And interestingly, they are actually just the same. Okay, you would have the same electric field. Okay, so I hope that is clear. So again, so this is basically what this is. Since R1 has 0 charges inside, therefore there is no electric flux, therefore there is no electric field. Because we know that the electric flux is the sum of all the electric field found inside your surface in the dot product of the differential of the area. And we've solved this from our previous discussion, and we know that this is basically equal to EA because the integral of a constant is still the constant, so we pull out the E, and the integral of a differential of an area is basically the sum of all the area, which gives us EA. And EA is equals to, according to Gauss's law, is equals to the total charges divided by epsilon naught. So we are going to focus on this equation to create a equation that we can use to solve for electric field. So we know that R2 has a charge Q inside and the electrical field has symmetry. Therefore, we can infer the electric field using Gauss' law, wherein from this equation right here, which is equal to, this is your Gauss law right here, right? So we're in the electric flux is equals to the total Q charge divided by the permittivity of free space, or epsilon naught. So what we're going to do is divide both sides by A, and it will give you this part of equation right here, wherein the electric field is equals to Q, or the total charge of Q, divided by the epsilon naught multiplied by the area. And since we have sphere here, our symmetry is in terms of sphere. The area of a sphere is actually 4 pi r squared. So we are changing this into 4 pi r squared, which give us the equation E is equals to Q total divided by epsilon naught, or permittivity of free space, 4 pi r squared. So this is the equation that we can use when we want to measure the electric field of an insulating sphere or an conducting sphere. There is another equation that we can use, but this time in a situation wherein you were given your charge density. So you use this when you don't know your charge density. But if you were given the charge density, you have to use this equation right here. For insulating spheres, where the charge are distributed inside its volume, we substitute rho is equals to Q over V. So remember, for insulating sphere, the charge is found inside. So if you have a sphere with a charge inside, therefore the charge is in terms of volume for insulating spheres. So what we are going to do is we have to take this equation right here, and we have to change the Q into rho V, because you are given the density or charge density. So we derive this equation from our equation of charge, volume charge density, wherein rho is equals to Q divided by the volume, where Q is equals to rho multiplied by volume. So we are changing this Q right here into rho multiplied by volume, and then the volume of a sphere, is actually 4 over 3 pi radius cube. So we're changing this V into 4 over 3 pi r cube, and what we have is we can cancel the r's, we cancel the pi's, and the 4 get actually cancelled. So what's left is your and then you have 1 r left there. It's your rho multiplied by the radius of your sphere divided by 3 epsilon naught. So this is the equation that you use if you are given the if you are given the charge density for insulating spheres. But what if you have a conducting sphere? So for conducting sphere, remember, for conducting sphere, the charges are found on the surface. For conducting sphere, you have to use the surface charge density. And the surface charge density is equals to sigma is equals to Q divided by the area. So what you want to do is use this. So you would have Q is equals to sigma area, and substitute sigma area for your Q here. So in the end, what you will have as an equation is is you would have something like E is equals to, let me just check for a second. So E is equals to Q total this time. So you have your sigma area divided by epsilon naught 4 pi r squared. And the area formula of a surface of a sphere is actually area of a sphere is 4 pi r squared. So that will give you sigma multiplied by 4 pi r squared divided by epsilon naught 4 pi r squared. So for insulating sphere, so the 4 pi r squared is basically done. So you have E is equals to your sigma divided by epsilon naught. So this is your equation for a conducting surface. So this is again this equation right here, these equations here is when you are given your charge density. For insulating sphere, you will be given a volume charge density. For conducting sphere, you will be given a surface charge density. And then you just have to use this equation to find the electric field. If none of these charge densities were given, then you would have to use this equation to solve for the electric field for a insulating or conducting sphere. I hope it's clear. Now let's put this into practice and let's have our sample problem. And for that, we have to move on to here. Okay, so let's read our equation. If a solid insulating sphere of a radius 5 centimeter carries a total charge of 150 nanocoulombs uniformly distributed throughout its volume, what is its A, volume charge density? What is the magnitude of the electric field at 10 centimeters and C 65 centimeter from the center of the sphere? So now let's try and solve this problem. So let's write our given. So here we are given that the radius of our insulating sphere is 50 centimeters, or that is actually equal to 0.5 meters. And then, since this is an insulating sphere, remember for insulating sphere, the charges are found inside the volume, not on the surface of the sphere. And the total charge that is found inside of that insulating sphere is equal to 150 nanocoulomb, or that is actually equivalent to, this is nano, 150 times 10 raised to negative 9 coulombs. Okay, so, and it is uniformly distributed throughout its volume. Then let's write what is being asked. So what is asked is what is the volume charge density. So first, what is the rho, or the volume charge density, and then what is the magnitude of the electric field, which is your E. So what is the E at 10 centimeters, and what is your E at 65 centimeters. And the drawing is actually already given to you. So this fully blocked gray circle is your insulating sphere with a radius r, and you have your first Gaussian surface with a 10 centimeter. This is your first Gaussian surface with 10 centimeter radius, and another Gaussian surface R2 with 65 centimeter radius. So how are we going to solve this? Well, we have to use our various formula. So the formula that we have to use is first, since we want to look for the volume charge density is equals to rho multiplied by Q divided by, since this is a volume. And then since we know this is an insulating sphere, and we are solving for the charge density, the volume charge density, then we can just use the equation E is equals to rho multiplied by the radius divided by 3 epsilon naught. This is the equation that we derived just earlier. Then this is what we use for a insulating sphere. For conducting sphere, remember, for conducting sphere, we use this equation where you have a sigma divided by epsilon naught. But since this is an insulating sphere, then we use rho multiplied by radius divided by 3 epsilon naught, or 3 permittivity of free space. And then another equation is we have an electric field is equals to the original one, where you have your Q total divided by epsilon naught 4 pi r squared. Okay, now let's do our solution. Let's solve this problem. So let's solve the volume charge density first. So how are we going to solve this? Well, we know the equation for volume charge density, which is equal to Q divided by the volume of your sphere. And we know that the volume of the sphere is actually equal to 4/3 4 pi r cube divided by 3. Let me edit this. So you have your Q divided by 4 pi r cubed divided by 3. This 4 pi r cube is the volume of sphere. So something that I want you guys to remember also. Volume of some various equations, area of a sphere, volume of a sphere, etc. And then what you want to do to solve for the surface volume charge density is basically just plug in your values. So your Q total is 150 nanocoulombs, so that is 150 times 10 raised to negative 9 coulombs divided by, you have your 4 multiplied by pi multiplied by radius r, which you have a radius of 0.5 meters cube, all of this divided by 3. And just plug everything on your calculator. You would get that the surface charge density is equals to 2.87 times 10 raised to negative 7, and this should be coulombs per meter cube. That is the units for rho, and that makes sense because you have your coulombs here and then you have your cube meter there. So that is the volume charge density. So after solving for volume charge density, now we can actually solve for our electric field. So for electric field at R1, so what is the electric field at R1 here? The thing though is we do not know how much Q is enclosed in it, because if the distribution of the charges are all over your insulating sphere, then if we are going to enclose only this part, meaning some of the charges that are found here are not found inside. And in order for us to find the electric field for this, we have to identify how much volume or charge is found in our Gaussian surface for R1. But that is that would be the problem. But something though is that this is where your surface charge or charge densities are important. So even though you do not know how much total how much the total charge is found here, what you can actually use to solve for E is the volume charge density, because this is uniformly distributed. By just using the volume charge density for R1, then you can actually measure the electric flux for or the electric field for R1. So the electric field for R1 is equal to, this is where you have to use this, you have your rho multiplied by the radius, which is your R1, divided by 3 epsilon naught. So that will give you 2.87 times 10 raised to negative 7 cubic per meter, or coulombs per meter cube, multiplied by R1, which is 10 centimeters, which is 0.1 meters, and then divided by 3, multiplied by permittivity of free space. The value of permittivity of free space is 8.8452 or 8542 times 10 raised to negative 12 coulombs squared per Newton meter squared. And just plug that out on your calculator. You would get that the electric field at R1 is actually equal to 1080 newtons per coulomb. And then at C, let's solve for the electric flux at R2. The electric flux for R2, as for R2, as you see, everything is basically enclosed inside. So, meaning the whole charge, the full total charge is found inside your imaginary Gaussian surface R2. So we have to use this equation right here, wherein you have your Q total divided by epsilon naught 4 pi r squared, and that is equals to 150 times 10 raised to negative 9 coulombs divided by 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared, multiplied by 4 pi r squared. R is 65 centimeters, which is 0.65 meters squared, and this is actually equal to 3191 Newton meter per coulomb, or Newton per coulomb. So that is the electric field at this distance, R1 or R2, and this is our electric field at a distance lesser than your radius. And we can get this situation by identifying your charge density, how much of the charges is found just within the R1. Okay, so I hope that is clear. We're gonna stop the video and this, and we're gonna continue the rest of because I don't wanna bombard you with a lot of information. I think this is enough. We are going to discuss the remaining symmetries next week. So you have your planar symmetry and your linear symmetry that we are going to discuss next week. So next week you wouldn't have a module uploaded. We will be using the module that is uploaded on Wednesday for our Monday discussion. So if you guys have any question about this, please do not hesitate to message me. Thank you so much, guys, and may you guys have a great day.